Hello, everybody. Welcome back to our third talk of our morning session of our second day of TWSS 2021. The next speaker that we have is Kathryn Wolfinger, and Kathryn is a graduate student at the University of Colorado at Boulder, where she works with John Cary on simulations of optical field ionization. So on that note, and I do want to make one quick announcement that if you have questions, there is a Q&A box at the bottom of your screen and you can type them in there. We will hold the questions until the end, but please, as you think of them, feel free to submit them and then Kathryn can answer at the conclusion of her presentation. Okay, now you can start, Kathryn.
All right, then, can you hear me?
You sound great, thanks.
Wonderful. So as Colleen said, I'm a current grad student at CU Boulder. I'm working with John Cary and Greg Warner. And my research has focused on simulating laser plasma interactions. So I'd like to give you a brief overview of what this talk is going to be about. I have two main topics that I'd like to address. The first, I'd like to cover plasma channels and introduce their use in particle acceleration. I'd like to talk about current formation mechanisms and the reliance on collision-based shocks. And then I'd like to introduce the PIC simulation I've set up through VSim to model this plasma column ionization and then channel expansion. Of course, I ran into some problems with that, with the feasibility, the cost of the run. So I'm going to talk then about speeding up the simulation by switching over to ePIC, which Luke Adams covered in the previous talk. The second topic that I'd like to cover are these electromagnetic pulses that I observed while simulating the plasma channel formation. I want to show PIC results that will allow us to look at the EMP as it propagates away from the plasma in comparison to the wake caused by the laser pulse. I'd also like to introduce a simple model that captures this EMP effect without the more expensive runtimes of the PIC simulations and the additional noise that we saw in those simulations. And then finally, I'd like to use that simple model to calculate energy values over a range of densities and laser aspect ratios so that we can see whether these EMPs are significant in comparison with the wake field. So first, most of you are probably very familiar with laser wake field acceleration, but I'd like to give a brief introduction to it. Essentially, as you can see in this figure on the right, when a laser pulse propagates through either a neutral gas, ionizing it, or a preformed plasma, the fields of that laser pulse create an outward force called the ponderomotive force, and it pushes both the electrons and ions away from behind the laser pulse. Of course, because the ions are more heavy, they stay behind, and you get a sort of plasma bubble, which creates these electrostatic fields. The most important of which, for my case, is this longitudinal field that will accelerate electrons forward into the plasma bubble, significantly increasing their energy. And if you've been at the earlier talks during this conference, it's already been mentioned, but VSim was actually used to simulate this sort of effect back in 2004, and it was the cover of the Nature Dreambeam article. Now, why do we want these laser wake field accelerations? Well, the basic reason is cost and size. We can achieve several GeV accelerations, and these things can fit within a university laboratory. And as such, they're much less costly than, say, an accelerator like SLAC. So the focus now is to increase these energies to get up to tens and 50 GeV, something that is really useful. What's one way we can do that? The answer is plasma channels, and I'll tell you why they are so useful. When we are accelerating these electrons in that plasma bubble behind the laser pulse, there are several things that limit the maximum acceleration that they're going to achieve, those being beam diffraction, dephasing, and pump depletion. And I'm going to talk about those first two. So in beam diffraction, you can see on this the right here, your typical plot showing the beam expanding over a Rayleigh length. And as that happens, the laser intensity is going to drop, and we're not going to get the same energy, the same acceleration that we want. And the best way to avoid that would be to provide some sort of waveguide that will keep the laser pulse focused. Of course, if we use say a sapphire waveguide, something physical, that's going to be damaged by the repeated laser pulses that you need in this setup. So the answer would be something like a plasma channel that isn't going to get damaged by those laser pulses going past. And the basic function of these plasma channels is that they have a low density center and then a high density edge. Some people call that a cladding. And because of the definition of the permittivity, that low density center is going to have a greater permittivity, and we're going to get laser confinement similar to what you might see with like an optical fiber. So this means we want low density plasma channels. But the question is, what about dephasing? Is that going to help us in that area, or is that going to hurt us? And the answer is that it's actually going to help us. So dephasing is when those electrons, they're relativistic, they're accelerating, and they start to outpace those fields that are accelerating them. And so you can calculate, you can approximate the time for those electrons to dephase. And it is actually inversely proportional to the plasma's density. So that means lower density plasma channels will both focus the laser pulse and achieve greater acceleration for those outgoing electrons. So now you may be wondering, how do we form these plasma channels? And the usual method is optical field ionization. I have a plot on the right that I've borrowed from a 2019 paper by Chalou. And you can see for a range of densities, these plasma channels, after they've expanded for about 4 nanoseconds. You can see that low density center and those higher density edges. Of course, as the density range gets lower, this is the about 1 to the 24 meters cubed, we start to lose that definition. So these are formed by a typical method of ionizing a column of plasma and then allowing it to expand outwards and relying on the collisions with the neutrals to drive shocks that form those edges. As such, it's highly reliant on the presence of shocks, which disappear at lower densities. It's not sufficient at lower densities. In addition, a lot of the simulation for this work, they may start with kinetics for the ionization of the plasma, but they will then deposit the energy and switch over to a fluid code to see the expansion of the plasma column. So why would we want to do this with PIC? Well, we'd be able to see the whole thing. We'd be able to start with the neutral gas, ionize the plasma, watch that fade away, and then see the plasma expand. And we would then be able to look at lower densities where shock formation is no longer viable. And you start to ask, well, where is that? When are fluid dynamics applicable? And when can we no longer use that to model this expansion? And one way you can look at that is the Knudsen number, which is supposed to be much less than 1. And that's a ratio of the mean free path to a significant length scale within your simulation. If I use some numbers from Chalou's plot, a density that corresponds to 50 millibar, about halfway between these two, you notice that you can get Knudsen number 1 with a length scale of about 12 microns. So we start to question, especially at these lower densities, whether fluid dynamics is going to be accurate or reliable for representing these, and then especially as we drop down to even lower densities. So what does my PIC simulation for this look like? I started off with 2D electromagnetic VSim. I put in a uniform neutral hydrogen gas, gave it a density that was similar to Chalou's work so that I could compare my results with his. And I sent in a circularly polarized laser pulse that propagates out of the page, so propagates in Z. And I tried to again replicate some of Chalou's conditions, but I did use a higher intensity. And for this simulation, I was able to get statistically significant particle ionization with only a couple particles per cell. On the right, you can see an example of that plasma density profile in this dashed line after the laser pulse, which is the solid line, has passed away. I think those units are wrong, sorry about that. But what I want to focus on here is that this ADK ionization, which is implemented in VSim, is very thresholdy. So we get full ionization, a strong flat top, and then right at this threshold, it drops off. The other thing that I included in this simulation, besides this optical field ionization that you're seeing the results of here, are impact ionization, and then those electron neutral elastic collisions that we need for channel formation at the higher densities. But this is when I ran into some problems, some non-physical constraints. I'm looking at 2 very different time scales. The ionization laser pulse is through and gone after about 150 femtoseconds, and the expansion we want to run out to 4 or 5 nanoseconds. The electron energies, they're about 10 eV on average, so we get a pretty small Debye length, about e to the negative 11, and that makes this simulation very computationally costly. The cell size, as you know, is restrained by that Debye instability, and the time step is restrained by the Courant condition. And so I started to, look at this problem and ask, how can we speed this up? So the first thing I did was look at the actual results for electromagnetic. And we needed to resolve the Debye length about 11K cells squared, and that gave us a very small time step of about e to the negative 17 seconds. So if we wanted to expand our plasma out to just 1 nanosecond, not even 3 or 4, we're going to need about 32 million time steps. And that just becomes not feasible for the length of a regular research project. So the first thing I did to address this was to switch over to electrostatic. I dumped the particles after the laser had passed, and I loaded them back in to an electrostatic VSim run. Now the time step is no longer limited by making sure light doesn't cross a cell in a single step, but instead making sure the particles only cross 1 or 2 cells. And that gave me savings of an order of magnitude. Now to reach 1 nanosecond of plasma expansion, we were down to 3 million steps. But that is still not feasible, that's not great. So the question became, how can I improve this further? And the answer actually came, through the work that was done by Luke Adams. I'm going to use his work with EPIC. If you missed his talk, please go watch it when it's up on the YouTube. It's very good. But essentially what this does is remove the limit to resolve the Debye length. And now you have to pick your cells to resolve the physics you're interested in. And so my number of cells decreased by quite a lot. My time step is down to e to the negative 14 seconds. And instead of 30 million time steps or 3 million time steps, I'm now looking at about 50,000 time steps. This is 60 times shorter than the electrostatic simulation. And this is something that I was able to run using the resources at NERSC. And so I'm going to show some of the initial results we have from this. The first thing I want to show is on the right here. I have again that plot from Chalou that I borrowed. And you can see on the left some initial results from my PIC simulation and expansion. They have the same radial axis, but the scaling on the density is slightly different. And my simulation is only run out to 1 nanosecond instead of about 4. But it's really great result because we can see the low density at the center and this high clotting. It's very promising. And my next step was to get the parameters that precisely match Chalou so that I can run this again and really compare with his results, especially at these lower densities, and see if we get the same effects. Unfortunately, those simulations are still running, so I won't be able to show them today, but I did want to mention that dropping my laser intensity to match Chalou's required an increase in the particles per cell use, and of course, made the simulation more expensive. But I did use this EPIC expansion code to look at one other thing. And I did a run at that low density where we don't expect to see any channel formation because collisions are no longer sufficient. This is the same laser parameters as in the previous slide. All I did was drop the density. And on this plot, you can see that expansion of the density profile over time. It starts off with that flat top density profile. And as it starts to expand out, we get some impact ionization and a little bit of collisional effects, but you can see that it's insignificant. And by the time we've hit about 3.5 nanoseconds, there's no channel, it's pretty flat all the way across, and this isn't going to work for laser wakefield acceleration. At this point, my next steps with this are going to be to look at other methods of channel formation that don't rely on collisions. Can we use secondary pulses? Can we use higher order pulses? And what's that going to look like when we run it in PIC? But now that I've covered that, I'd like to move on to the second part of this talk. In this time, I'd like to talk about the electromagnetic pulses that I noticed while doing those plasma channel simulations. And then I'd like to show you those PIC simulations and the simple fluid model and look at those energy values. So let's jump into that. Now I'm going to need to switch over so I can start that video for you guys. So basically, our plasma is right around in here, and you can see this single pulse EMP propagating away from the plasma. I'll play that again. And when I first saw this, I thought, oh, it's some sort of numerical issue. Maybe we're not resolving something enough. But it is present, and we wanted to explore this. And so we thought, here we see it at a lower density, and it's a single pulse, and we are getting a couple millivolts per meter. What happens if we increase the density? What's this going to look like? Here we go. And we found out that this EMP shows very strong density dependence. So I'm going to play this video for you. And as you can see, instead of a single pulse, we're getting a repeated ringing structure propagating away from that plasma and out into the simulation. And this raises the question of whether we can use this as a diagnostic, whether it's reflective of the plasma density or other properties of the simulation. And one thing I'd like to point out is that the EMP frequency is very close to the plasma frequency. For this case on the right here, it's about 80 terahertz. So now we're looking at this and we wonder, how significant is this EMP? We'd like to look at the energies of it compared to the wake field left behind by the laser pulse. And to do that, we're going to need to make a transfer into longitudinal PIC and away from this transverse slice. So instead of having the laser pulse propagate out at us, we'd like to move the simulation along the side of the pulse. So as I mentioned, the same laser parameters as we used before are going to be used here. And we're going to use a longitudinal geometry instead, with lasers propagating in X. And we'll have a moving window that's traveling with the laser. So we get sort of stable results. And in this case, again, we get a plasma slab with a radius of about 35 microns. And you can see that in the next plot. So here we have those PIC results for two different densities. I have the low density case on the left and the high density case on the right. And you can see a couple orders of magnitude difference in amplitude. And on the high density case, we can see that ringing structure of the EMP. This is the plasma column in the center, the fields within that plasma column. And you can see that EMP propagating outwards. In the high density case, in the low density case, we can see that again, but here it's more of a single rise and fall with a small, perhaps secondary. So it's, again, we're seeing that dependence on density that we had seen before. And then what the problem with this became the run times, of course. This is, we want to be able, especially in this high density case, to be able to resolve these small oscillations. We're going to need quite a few grid cells. This is about 10 particles per cell. When I went to the lower densities, we needed to make sure we could still see the EMP, so I had to boost that up to about 50 particles per cell. And these runtimes are quite long, and we were seeing a lot of noise, especially in the lineouts when we're trying to look at this cross sections of this EMP. And so the question became, is there some sort of reduced simple model that will still show us this EMP without all the noise and with the quicker runtimes? And the answer is a simple fluid model that's driven by the ponderomotive force with a term from the laser envelope. So we have your usual ponderomotive term. And if we look at the electric field that I'm using in those simulations, we've got an X component within the temporal exponent. So that when we take the X derivative of that, we're going to get a term that's proportional to the laser pulse envelope. And it's going to be in the direction of the laser propagation. It's going to be our driver term. When I simulated this in 2D, even though there is a ponderomotive force in the Y direction, I actually left it out because our A naught value is much less than 1, so we're not going to see a big blowout of the electrons behind the laser pulse. And I really wanted to see what the simulation would look like if we're only considering this driver right here. For the simulation, I just want to mention, we didn't start with a plasma column. We actually included the ionization in the steps. It was simple to do with the ADK model and then insert into the plasma frequency. We used a finite PDE solver to get the results of this simple model and then compare it with the PIC, which I'm going to show you on the next slide. So here we see I have that low density case. This top plot you have seen before. This is the PIC results for the lower density, about 6e to the 16 in centimeters. And here's a still from the 2D model at the same point in X. And you can see really great agreement with this edge here and with the location of this oscillation within the plasma. At this point, I'd like to point out something I had forgotten to say earlier, which is that these oscillations within the plasma do correspond to the plasma wavelength, as is expected. So when we take the lineouts of these two plots, and we look at that on the right here, the PIC is the black and the 2D model, the simple model on the bottom is going to be the blue line. And we see that we get agreement with the location of the troughs and the peaks, and there's only a slight offset in the amplitudes. So that is really promising. And the question becomes, what does this look like at higher densities? Do we also get similar agreement? Can we use this to do energy calculations? Excuse me. And we can see that the answer is, again, yes. So we get similar amplitudes. Again, these plots both have the same Y amplitude, and you can see at, say, 150 microns away, we're getting about 50 e to the 8 volts per meter in the electric field. And we get similar frequencies as well. So now we have this less noise, and can we use this to estimate the energies? So for the wakefield, I'm going to do a spatial integral over the energy density, about 1 plasma wavelength. And then for the EMP, I'm going to do a time integral over the pulse's flux through several different cylinders that are larger than the plasma density itself. And I want to know, how does this energy depend on density and laser profile? Is it significant? Are there certain areas where it's significant and others where it's not? So to do that, I'm going to look at 5 different aspect ratios. They range from a very long pulse in time with a very short width. So you can call that a cigarette or cigar if you want something easy to refer to it as. And then we have our sphere where it's like a 1-to-1 ratio. And as it gets skinnier, it becomes more of a pancake or a crepe where it's very wide, it has a very large radius, but it's very short in time. And I looked at a range of 5 densities for these energy calculations. I wanted to consider a range within the values I've been using for those plasma channel simulations. What am I going to hold constant for these calculations, though? I decided the best thing to hold constant was to ensure that the pulse length is matched to the plasma period. And so using that condition, I was able to determine my full width half max in time. And then I can plug in my aspect ratio to figure out what the width is. So this can be adjusted for all the densities, but we're still maintaining this relationship between the pulse length and the plasma period. And what do those energies look like? Here are those results. And you can see on the left, again, we have that very elongated laser pulse. And then as we move to the right, that becomes much flatter and much wider. And they all have the same Y scale, and you can see the EMP energies in this solid dashed line and the wakefield energies in the dotted line. And the first thing I want to point out is that as long as you're holding the aspect ratio constant, we are seeing that the wakefield and EMP energies are fairly independent of the density, but that the wakefield energy will rise as you increase the aspect ratio, while the EMP drops slightly. And the question, I had from the beginning is this EMP significant? Well, if you look at this very elongated pulse, you'll see that the EMP energy is actually larger than that of the wakefield. And for something that's a more realistic laser pulse shape, the EMP is actually about 25% of the wakefield energy. And here it's down to 5%, here it's down to 1%. So the answer is that, yes, the side effect that I stumbled upon while looking at those plasma channel expansions is actually quite significant. It both carries a fair bit of energy and it has a frequency that can tell you about the density of the plasma that emitted it. So in conclusion, EPIC has enabled us to do VSim models of plasma column expansion. We were able to get around those time restraints based on the Debye length and based on trying to include both ionization and expansion in one single simulation. And then at those lower densities, we did see the shock formation fail to form the channel. And that is an area where we could get a lot of acceleration if we're able to form channels at those lower densities. So that's an area of further work. And then both these electrostatic wake fields that arise from the laser plasma interaction and the electromagnetic pulse that I've seen propagating out can be seen within PIC, within transverse PIC, within longitudinal PIC, and within simple fluid models based just on a ponderomotive driving term. And if you look at the ratio of that EMP energy compared with the wake field, while it does vary with the laser's aspect ratio, it is rather significant for those more elongated pulses. Thank you for listening to my talk, and I'll be happy to take any questions.
Very nice, Kathryn. Thank you so much. It looks like I'll go ahead and start. I have a couple questions that were sent to me directly. So about plasma channel formation, you've only been simulating plasma channels in 2D while the actual structures are 3D. Do you feel like that approximation is valid?
Yeah, that's a good question. If I go back to some of those plots, if you look at this, I'm only doing a 2D simulation, and of course the plasma channel expands and has quite a long length. And this approximation is actually valid as long as the column length is much larger than the radius of these channels. And in most cases, these radii are tens or hundreds of microns, as you can see here, while the column lengths are many centimeters. But it is a goal, especially when we look at those lower density cases. If we can find a method that produces a channel, we will then explore it in 3D as well as 2D.
Okay. About the electromagnetic pulse, is the EMP behavior dependent on the polarization of the laser pulse?
That is a good question. I hadn't mentioned that before when I'd shown this EMP. And we did an exact same simulation where the only thing we changed was the polarization. We kept the same laser spatial profile as well as the max intensity. And you actually see no difference in the outgoing EMP. So it is in fact independent of polarization.
Okay. If anyone has any additional questions to ask Kathryn, you can type them in the Q&A box on the bottom of the screen. I just want to let everyone know we are recording all of these talks. Our goal is to get those up on YouTube next week, hopefully, so you can refer them, as well as presentations could be available upon request as well, or if there's specific documents, I may be able to get those to you. And then, of course, I have to give my plug, which is if you want to evaluate VSim for 30 days. If you go to the TechX website, you can request a 30-day evaluation. VSim, RSim, the latest versions of those products. And our website is txcorp.com, txcorp.com. And that's where we can get you an evaluation. But really, well, very nice, Kathryn, very well put together. So
I have a question. So Kathryn, this is awfully funny coming from me since you and I are collaborating.
Mm-hmm.
But your EMP energy, just to clarify, that was per unit length?
Yes, correct.
Or was it per plasma wavelength?
That is per unit length of the plasma column.
Okay. Interesting. Okay, good. Thank you.
Sure.
Of course.
Any additional questions before we end for our morning session today? We will be starting up again this evening in 5:30 Mountain Time in Colorado. We have two different presentations tonight. We are going to start out with Dr. Daniel Main who is going to be speaking. I'll just pull this up real quick. Daniel Main is going to be speaking at 5:30 about using VSim to model electromagnetic propagation through collisional plasmas. And then we'll have Dr. David Smith at 7 p.m. Mountain Time talking about using VSim to model THZ terahertz microstructures, and plasmonics. So we will be back at that time. Any final questions? Okay. Well, I think we're good. Thank you, everybody. We will be back online at 5:30. Thanks, Kathryn.